So thank you for that introduction. My name is Tim Stevenson from Ionix. I thought I'd have a catchy title to try and attract people to come with ultrasonics in the danger zone. Quite how we're going to get there at the end, we'll work it out, but we'll start at the beginning and see where we land. So a bit of an introduction to myself and our company, just to sort of set the scene. So Ionix is based in the UK, in a city called Leeds, so in the north, not too far from Manchester. And what sets us apart, I guess, with our ultrasonics is we actually manufacture a unique piezo crystal that's in the heart of all of our transducers. It's been developed and designed for what we would call extreme environments, and those extreme environments aren't just high temperature, but that's primarily what we're going to talk about today. And then we take those raw materials, manufacture everything in-house through to the sensors, and then integrating them into different systems. And that could be anything from ultrasonic flow to what we're going to talk about today, NDT. We've recently opened our new facility in Leeds. So we have both the advanced materials manufacturing facility and extreme environment sensors centre of excellence. And that's happened this year, so it's been a great step forward for us. So our NDT ultrasonic testing technology is based around being able to access and enable technicians to do inspections in extreme environments. Quite why that's missing off there, I'm not sure, but it covers this range of what we call extreme environments. So high and low temperatures, everything from cryogenic all the way up to nearly 1,000 Fahrenheit. Intrinsically safe for explosion-proof sensors, radiation resilience for use in the nuclear industry, high pressure, very robust sensors for things like subsea or mining. And then we pride ourselves on having some of the highest sensitivities to be able to penetrate some of those materials in those extreme environments, but maintaining the plug-and-play compatibility with commercial flaw detectors, gauges, things you already use. So we're not trying to reinvent the wheel. Why do we need this type of technology? So if we think about refineries and the damage mechanisms in those kind of locations, then I would say sort of represents those extreme environments. Obviously, they're surrounded with gas and vapors, so there's explosion risks. But the primary one would be things like high temperature, and the API, American Petroleum Institute, defines high temperature in those areas for the damage mechanisms as over 400 Fahrenheit. We have these typically uniform damage mechanisms, things like corrosion, oxidation, and sulfidation being one of the big ones. It's important when we look at those, we're designing tools to look at those damage mechanisms, and so it's just good to sort of understand what's that type of damage we're seeking. And as an example, sulfidation, it's the most prevalent damage mechanism in the oil refining industry. Everything that those hydrocarbons touch that's iron-based forms a passive layer of iron sulfide above 260 centigrade, about 500 Fahrenheit. The danger of sulfidation is because it's uniform wall thinning, it's catastrophic when it fails. It doesn't leak like pits do. So it's a damage mechanism we need to get a hold on. And you can see that by the API recommended practices in 2020 now require identification of those hydrocarbon circuits that are at risk from low silicon content that prevents the sulfidation. And this is really where we got started looking at these tools back in sort of 2020, 2021, sulfidation being the case study to start with. So what we ended up developing are things like ultrasonic testing tools. So we'll start with a simple dual element wall thickness transducer. It's an ultrasonic technique, it's relatively low cost. We do a range of frequencies, but the three takeaway things from this type of technology is we can offer 2 to 3 times the wear resistance. That allows us to be able to put it onto crawlers and scanners or to do scrubbing. Perfect for when you're looking at those damage mechanisms like sulfidation. We can operate without duty cycling, without cooling across quite a wide temperature range. It's really important, so we can cover those areas prone to risk of sulfidation without having to shutdowns or isolation of that unit. And we've managed to give them that increased sensitivity to get through thickened components or high temperature components where you need that additional that punch to get through. We're in the TPAT room, so here's some data from the TPAT pilot, just for example, just showing you what the sort of typical responses are at that kind of 500 Fahrenheit temperature, where we're looking at damage like sulfidation. Oh, sorry. So lots of people have sulfidation damage, and we spent a lot of time working with owner-operators to make sure that we can get accurate and reliable, repeatable wall thickness measurements by doing things like coming up with procedures for compensation and calibration. Give you some examples. As we increase the temperature of things like steel, the velocity is going to decrease, and we have to compensate for that. There's standard compensation algorithms or process procedures defined in ASTM, E797, and the ISO standard. If we give that by example, take a piece of steel with a set velocity, take our wall thickness measurement, ambient temperature, and we get 0.414 inch. If you take that measurement at 470, our gauge will give us a reading of 0.427, so it's not correct. We can apply the correction from ASTM, and you'll see we've still got quite a bit of a difference there, or sufficient difference that lots of people don't see that as reliable or repeatable. If we use the ISO correction, you can see we can get much closer. We spent a lot of time then looking at different metals, different steels, to plot that out and understand how do we compensate effectively. And the reason is the ASTM standard is broad, and it overcorrects because it's trying to cover all steels. So you can see here on this solid black line, the hotter we get, the more it overestimates. So it's doing it the right way, but it's often giving us the wrong number. We've taken some actual measurements of steel here. You can see it matches very much better with the ISO standard, but we've ended up taking different metals, Inconels, titaniums, steels, stainless steels, and we publish now those correction factors that you can slot straight into your gauge or into your flaw detector. If you want some more information on those, there's some nice videos of that with standard commercial gauges, flaw detectors. They're on the website. You can use those to have a look, and then how we use those tables more effectively. But I don't want to go through all of those just now. We sent a lot of this through independent testing through the Hoist Group. This is a joint venture, I think that's the right word, or it's a consortium, lots of owner-operators. It's based out of the UK, but it's transatlantic. So we offered a lot of our equipment up to the participants, so service providers, other vendors, manufacturers of high temperature equipment to put it together and see it working. The report's quite good. I'd recommend anyone that's interested in high temperature to get a copy. I think it's free if you're a member or if your institution's a member. Otherwise, I think it's only a few $100s to get a copy. But hopefully you can see that with kind of the scanning tools that exist now, we can get data that's as good as ambient temperature. This is taken at above 400 Fahrenheit. And there's some good advice and recommendations on things like which couplants to use, how to do the compensations, do the zero corrections, and then advice on things like the probability of detection for certain pit aspect ratios, defects. And you'll see, we've taken some of that on board. We have different range of frequencies now and diameters to compensate for things like pitting and other areas. Talks a lot about things, procedures to reduce noise. As we start to increase the temperature of steel, that velocity is going to come down. Our wavelength is becoming closer to 10 wavelengths of the grain structure of steel. So you're going to start to see that scatter increase. So there's some good advice there on how to either change the frequency or change your settings to try and reduce that noise and increase the signal to noise ratio. Some examples then, real world scenarios of mapping sulfidation using a range of different vendor equipment, but this was an example from a parvirus NDT. So you can see very good detail here taken of sulfidation. You can see those uniform areas of wall thinning as you'd expect. Again, all this is taken in service at that high temperature, 500 Fahrenheit. So this is actually taken on a piping circuit, 6 to 8 inch. And you can see here, this is all then compensated using those curves beforehand to get accurate data, and it matches within plus or minus 0.002 inches of the ambient temperature measurement. So it's pretty good. Where does that take us? This is all very, I guess, relatively simple wall thickness measurements either by hand or on a crawler. Where else can we take this technology? So we've been deploying this on my roadmap onto drones. So this is a nice example of this is a flare stack inspection. So particularly where you've got the two mismatch of metals in a flare stack often gets missed, or it's very costly to put the scaffold up to inspect those areas. It's a great example of where drones can do that using the high temperature technology. We've put it into time of flight diffraction, so looking at weld root erosion, defects in welds. So this has become more and more prevalent now in the nuclear industry, where we're verifying those welds at temperature, either during the weld to try and save time, or very soon after. So we're surviving those temperatures, those weld temperatures as it's being conducted. Good example here of some intrinsically safe, so tank inspections. This is an EX robot with a Cygnus EX gauge, and then with the transducers on there as well. So it's an entirely intrinsically safe package. So we're able to access those areas that typically would have to send people in. We can remove those from the tank now. And then this is some of the data from the Quasit HoloLens. We can see we're doing virtual grids. It's all getting very clever, using different types of transducers then to encode to doing grid surveys. The holy grail, though, for us, I think, as we see more and more, is getting into high temperature phase array. So we have now cooled wedges, so you can take any commercially available linear array, put it on, start doing corrosion mapping up to 400 Fahrenheit. So just under that sort of area for sulfidation. But these then are sort of latest phase array. The whole unit is uncooled, and we can go back up to those temperatures, 670 Fahrenheit. So again, no duty cycling. It makes it a lot easier now to start doing lots of different inspections in service, rather not just corrosion mapping. We can start to do weld inspections and everything else that comes with the advantages of phase array. So there's some areas to watch out for. Oh, my voice is actually going. So that leads me to the last slide, which was, I guess, was my highway to the danger zone, and hopefully trying to show how using new technology to access these dangerous or places that we may want to send people to less, to be able to take these types of measurements, and just sort of give you a flavour of what we've been doing with TPAC and others to get there. Then going forward, some of our latest is we're now starting to look at taking that same technology into subsea, so higher depth ratings to do TOF phase array, etc., and just sort of exploring where else we can take the technology. I'm sure you guys will have lots of other examples we can look at. And I'll leave it there before I can't speak anymore. I'll take any questions. Thank you very much.
Thank you, Dr. Stevenson, for your talk.